TOHSBAH1 October 26, 1999, J Tosei 1E9WWW09 NIT U.S. Patent 00091029P, 3INS is 3DXV3D. 593-999-1 Acoustic Canon Background of the invention 1. Field of the invention. This invention relates to an acoustic device that emits repetitive sonic pulses capable of dispersing or incapacitating a biological target. More particularly, a planar array of multiple acoustic pulse sources cooperates to generate highly focused pulses of high-intensity sonic energy over a small area. 2. Description of the related art. Military and law enforcement personnel have a need for non-lethal weapons. Such weapons are useful in riot control to disperse a hostile crowd. In sniper and hostage situation, a non-lethal weapon provides a means to neutralize a hostile target without collateral damage to hostages, bystanders, or property. In combat, a non-lethal weapon is useful to neutralize sentries and warning devices. Since the weapon produces casualties, rather than fatalities, each hit removes 3 opponents, the injured and a 2-person rescue squad, from the combat zone instead of the 1 person removed by a fatality. High-intensity sound pulses have a debilitating effect on biological targets. Humans become disoriented by exposure to sonic pulses exceeding a threshold of pain of about 150 decibels dB. Eardrum rupture occurs at about 190 decibels, the threshold for pulmonary injury is about 200 decibels and the onset of lethality is about 220 decibels. U.S. Pat. No. 3,557,899 to Longinetta al. Discloses a parabolic reflector that focuses and transmits a continuous sound at a frequency of between 8 kHz, KHZ, and 13 kHz. Within this frequency range, sound attenuates rapidly and the disclosed device is believed effective only at close ranges. The U.S. Pat. No. 3,557. 889 patent discloses utilizing the device in close proximity to a riot or in enclosed areas, such as a bank vault. U.S. Pat. No. 4,349,898 to Druis al. Discloses a sonic weapon to destroy buildings and disable personnel. A plurality of tubes each conduct a continuous sound generated by a jet engine. Rotating fans at the ends of the tubes create pulsed sound of a desired frequency. The fan speeds are set such that each tube has a pulse sound frequency 2 times the frequency of a preceding tube, leading to an additive effect of sound waves referred to as a parametric pump. The disclosed device appears heavy and requires careful alignment of a number of large apparatus for operation. There remains, therefore, a need for a portable acoustic weapon capable of dispersing or disabling biological targets at distances of up to 100 meters that does not suffer from the disadvantages of the prior art discussed above. Summary of the invention. Accordingly, it is an object of the invention to provide an acoustic device capable of dispersing or incapacitating a biological target. One feature of the invention is that the device has a planar array of simultaneously actuated acoustic pulse sources. Interaction between the sonic pulses forms a Mach disc. A second feature of the invention is that the device is actuated by either a shock tube or detonation of an explosive chemical mix. Among the advantages of the invention are that the Mach disc is a compact packet of sound that may be accurately fired to minimize harm to hostages, bystanders, and property. The Mach disc effectively incapacitates or disperses a biological target with a minimal threat of lethality. The 1525-35-40-45-50-55-60-652 acoustic device is relatively lightweight and is readily transported by an infantry vehicle and operated by a single person. In accordance with the invention, there is provided an acoustic cannon that has a plurality of acoustic sources arranged in a planar array about a central point. Each of the plurality of acoustic sources has an input end and an output end. The input end receives a sonic pulse and the output end transmits a sonic output. A sonic pulse generator is coupled to each of the input ends, and a timing mechanism is coupled to the sonic pulse generator such that the sonic pulse is received by each of the input ends at substantially the same time and is of substantially the same frequency and duration. The combination of the planar array and the parameters of the sonic output effectively generates a Mach disk. The above stated objects, features and advantages will become more apparent from the specification and drawings that follows. In the drawings, Fig. 1 shows in cross-sectional representation a single sonic source as known from the prior art. Figs. 2a and 2b illustrate the acoustic canon of the invention. Fig. 3 illustrates in cross-sectional representation an acoustic canon in accordance with the first embodiment of the invention. Figs. 4a through 4e graphically illustrate the generation of a sonic pulse through the use of a shock tube. Fig. 5 illustrates in cross-sectional representation an acoustic canon in accordance with a second embodiment of the invention. Fig. 6 graphically illustrates the relationship between frequency content of the sonic pulse and directivity. Fig. 7 graphically illustrates the relationship between frequency contained in the sonic pulse and attenuation. Fig. 8 graphically illustrates the relationship between pulse range and peak pressure measured in decibels. Detailed description. Fig. 1 illustrates in cross-sectional representation a muzzle portion 12 of an acoustic device 10 as known from the prior art. A sonic source, not shown, generates a pressure wave 16 that is transmitted along an interior bore 14 and emitted from an output end 18 as spherically expanding sound waves 20. The spherically expanding sound waves 20 diffuse rapidly. The prior art acoustic device has limited value as a weapon. The strength of the pressure wave 16 drops to below useful values within a very short distance and time. Additionally, the spherically expanding sound waves 20 diffuse over a broad area, rendering target selectivity difficult or impossible. The disadvantages of the prior art are resolved by an acoustic canon in accordance with the present invention. Fig. 2 schematically illustrates a portion of the acoustic canon of the invention in front, Fig. 2a, and side, Fig. 2b, views. Acoustic sources 22 terminate at an output end 24. Interior bores 26 extend from output ends 24 to input ends 28 that are adjacent to a sonic pulse generator 30. A timing mechanism 32 controls the rate and duration of generated sonic pulses. In a first embodiment of the invention, the sonic pulses are generated by detonation of an explosive mix, and a fuel storage chamber 34 is provided to house required quantities of the additional explosive mix, or explosive mix precursors. 5,973,999 3. The front view, Fig. 2a, illustrates the output ends 24 arranged in a generally planar array having symmetry about a central point 36. The planar array may be configured as any shape, with symmetric shapes preferred to optimize the sonic output. A most preferred configuration is elliptical, including circular arrays. The number of output ends 24 in the planar array is at least 2 to provide directivity and at least 3 to provide a symmetric array. Preferably, there are at least 4 output ends 24 in the planar array. More preferably, there are from about 10 to about 40 output ends, and most preferably, from about 20 to about 30 output ends, as illustrated in the side view, Fig. 2b, when sonic pulses of substantially the same amplitude and duration are emitted from each of the output ends 24 at essentially the same time, the shock waves 37 interact along a longitudinal axis 3, running parallel to the longitudinal axis of the interior bore 26 and extending outwardly from the central point 36. Interaction of the shock waves 37 from the plurality of output ends 24 generates a Mach disk 39. The output has some of the characteristics of an acoustic soliton, although while a soliton does not change shape with propagation, the shock-driven output pulses of the invention are expected to undergo relatively slow and predictable changes in shape. The Mach disk is a nonlinear shock wave that travels rapidly along the longitudinal axis 3 with limited radial diffusion over distances of up to 100 meters. The intensity of the shock wave 37 contained within the Mach disk 39 decreases more slowly over distance and time than the range behavior of a single spherical expanding pulse. If the same energy is used in a multiple tube source having a planar array of outputs as in a single output source, the on-axis peak pressure for the multiple tube source, in the direction of maximum directivity, is n degree times that of the single tube. The n factor is derived from a linear superposition of the predicted pressure pulses from individual sources, which will all be of shorter duration than a single pulse derived from a single source using the same total energy. With multiple sources, energy from each individual source is concentrated in a shorter on-axis pulse. At the same range from the array, the resulting peak pressure is greater by this factor compared to the peak pressure associated with a single source of equivalent total energy. The attenuation rates of the peaks with distance will be essentially the same for single and multiple sources. For a 10-tube array having the same output energy as a single tube, the sound pressure along the longitudinal axis is 4.6 times higher than for the single tube at similar times and distances. Fig. 3 illustrates in cross-sectional representation an acoustic source 44 use with the acoustic canon of the invention in accordance with one embodiment. The acoustic source 40 has an input end 42 and an output end 44. The input end 42 receives sonic pulses and the output end 44 transmits the sonic output as a portion of a planar array of outputs to generate a Mach disk. Coupled to the input end 42 is a sonic pulse generator 46. The sonic pulse generator 46 detonates an explosive mix of gases or vaporized liquids. A first fluid component, that could be a gas, a liquid, or a mixture thereof, is delivered to a mixing chamber 48 through a first conduit 50. A second fluid component is delivered to the mixing chamber 4 through a second conduit 52. A first fluid control valve 54 and a second fluid control 56 determine the ratio of first fluid to second fluid in the mixing chamber 48. While stoichiometric ratios of the fluids are preferred, a stoichiometric ratio 1525, 35, 40, 45, 50, 55, 60, 65, 4 is not required. Any fluid mix ratio that generates an explosive shock wave on ignition is suitable. A third fluid control valve 58 introduces a desired volume of mixed fluid into the barrel 60 of the acoustic source 40. The desired volume of fluid substantially fills the barrel 60. The fluid control valves 54, 56, 58 or any suitable type of fluid metering system. Since the first fluid control valve 54 and the second fluid control valve 56 control fluid ratios, adjustable manual valves are suitable. The third fluid control valve 58 accurately and repeatedly delivers the mixed fluid to barrel 60. Rapid repetition rate is frequently required and the third fluid control valve 58 is preferably an electrically actuated solenoid valve. A power supply 62 generates a voltage potential between electrodes 64 that exceeds the breakdown voltage of the mixed fluid contained within the barrel 60, thereby generating a spark at gap 66. An effective voltage potential is from about 10 kV to about 100 kV. To optimize generation of the Mach disk, the interior bore of the barrel 60 is preferably symmetric about a longitudinal barrel axis 68. More preferably, the interior bore is circular in cross-section and the spark gap 66 aligned along the longitudinal axis 6. A timing mechanism 70 is coupled to the sonic pulse generator and controls power source 62, third fluid control valve 58, are preferably both devices. The timing mechanism 70 ensures that each of the plurality of acoustic sources is fired at substantially the same time for effective generation of the Mach disk. A number of different fluid combinations produce effective shock waves that exit the acoustic source 40 as a strong sonic pulse. Preferred fluids are combinations of gases and include hydrogen, oxygen, propane, air, acetylene, oxygen, acetylene and the like. A preferred explosive fluid mixture is hydrogen and oxygen in approximately